Okay, welcome everyone. Nice to see you all again. It's been a while, I guess, with the elections and the quiz. It's been 3 weeks since we saw each other live, so it's nice to be back. So, as I announced earlier this morning, so the plan for the next week during these recitations and discussions is to really focus on reviewing the material that will be covered in the upcoming quiz next week. So today we'll be solving a number of problems from the area of probabilities and combinatorics. And before we dive into that, I have a couple of announcements first. So we posted the quiz for grades. And then as usual, you have 1 week, meaning until November 24th, to file a regrade request on Gradescope for quiz 4. And then as we started doing a couple of quizzes ago, we also solved a couple of quiz 4 problems during discussions last week. And I believe Mark posted some of them to Piazza as well. So if you're curious about solutions for quiz 4 problems, you can take a look at either the discussions video from last week, or you can look them up on Piazza.
There aren't any on Piazza.
Where did you put them?
We just put the hardest ones in the discussion. People did well.
Okay, got it. Okay, I see. I misread your announcement. Okay, thank you, Mark. So scratch Piazza. Yeah, one more thing I want to add. So if the question you're interested in wasn't covered during discussions, then feel free to come to office hours or message us and we'll help you out to solve it. So that's quiz 4, and then quiz 5 will be next week. So that's November 24th. And as usual, it will be 1 hour. However, it will be between 7:30 a.m. and 5 p.m. So we extended the time a little bit because a few students requested that. So, you can start as late as 4 p.m. and still have 1 hour to solve it. And the quiz will be on counting and probabilities. So we'll review this material today. TAs will review it on Thursday. Today we'll mostly focus on counting. TAs on Thursday will mostly focus on probabilities. And then on Monday, there will be kind of a last minute quiz 5 review session, similar to the one we did before quiz 4. So we'll announce that as well. So you'll have plenty of opportunities to prepare for quiz 4 and practice problems and so on. And I strongly suggest that you take advantage of those. So finally, we're a little bit late with grading. Homework 5 and quiz 5 just kind of in quiz 4 landed around the same time. So we're still not done with homework 4, but we're working on it, and we'll definitely have it done by this Friday so that you can take a look at what you did wrong and still study before the quiz. Okay, so another thing I want to show, we always post this, I always show this. So this is the breakup of the scores for quiz 4. As you can see, I mean, the class did really well on quiz 4. So that was great to see. Okay, before we start working on the problems, any questions about the announcements, about the class? Okay. So we'll start with a couple of, really easy ones. And then we'll move towards more complicated problems. So this is an easy one, and I'll give you like 1 or 2 minutes to try to solve it on your own. If you are struggling already with this one, you should really catch up with this material. You know, this is a really easy question. Okay, so I'll give you a minute or two to try to solve it, and then we'll do it together. Okay, so there is even a hint about the question. You can use multiplication principle to solve it. So we have 4 choices for the appetizer times 5 choices for the main course times 3 choices for dessert. And that's equal to 60. So you have 60 different choices to select your dinner, your meal. Okay, any questions about this one? Okay. Okay, so this should be an easy one. Let's see. So I'll actually skip this one. I think it's a little bit less interesting. So let's now do a couple of problems that use permutations and combinations. So this is a quick reminder. You know, we denote permutations with P, and they take n and k as the argument, and then you compute them as n factorial divided by n minus k factorial. And then combinations, we denote them with C, n comma k, and we compute them using this. So n factorial divided by k factorial times n minus k factorial. So these are the formulas. When do we use them? So we use permutations when the order matters and repetitions are not allowed. And we use combinations when the order does not matter and repetitions are not allowed. So when you see a problem, and I repeated that a couple of times during lectures and previous recitations, the first thing you have to establish for a problem is, does the order matter and are repetitions allowed? And based on your answers to these 2 questions, you will select the appropriate structure that you will use for the problem. Okay, so let's solve a couple of problems that use permutations and combinations. So this is another easy one. So 10 kids are getting in line to buy ice cream. How many different ways are there to form a line? So I'll give you 2 minutes to solve this. I'm not expecting for you to calculate the final number here. I would just like to see the expression that gets you there. Okay. So the solution, so okay, so they're forming a line. And so the order matters, right? I'm sure you know, if you ever stood in a line, you know that there is a big difference between being the first person in the line and the last person in the line. So the order matters when you're forming a line. And the repetitions are not allowed. You can't put the same kid at two places in a line. Like you can't copy them, right? So these are permutations. And this is kind of the thought process how you establish that there are permutations. In the quiz, of course, you know, we're not going to give you a hint, you know, is this permutations, combinations, or whatever. You'll have to establish that on your own. And so we are choosing from 10 kids, and we are creating sequences of length 10. So it's P 10, 10, and that is equal to 10 factorial divided by 10 minus 10 factorial. That is equal to 10 factorial divided by 0 factorial. So this might look a little bit weird at the first glance, but from the definition of factorials, we know that 0 factorial is equal to 1. So keep that in mind. So then this is equal to 10 factorial, which is some gigantic number. Okay, so that's the solution to this one. Any questions? By the way, I should have said it earlier. You know, these days we have around 20, 25 students joining these recitations. And so you can write your questions in chat. And I've seen that, you know, some people are already doing that. You're also more than welcome to speak up and just ask your question. So you can just unmute yourself and ask a question. Okay, great. So, you know, this is another easy question. I'm just kind of trying to qualify them a little bit so that you know what you can expect on the quiz. So on the quiz, I would consider this to be a really easy question that, you know, you should be able to solve in like 2-3 minutes at most. I already mentioned this before. I'll say it once more. In the quiz, and Mark, you should remember this so that I don't forget it. We will give you a hint whether we are looking for, you know, the final calculated number or whether you can leave it kind of in this form. And that will depend on how big the number is, basically. You know, anything under 1,000, probably ask you to calculate it out. More than 1,000, you can kind of leave it in this kind of expression form.
Yep. No calculators.
Yeah, no calculators, and so you don't have to worry about, oh my God, how the heck I'm going to calculate, you know, 50 factorials or something. We're not going to ask you to do that. All right, thank you, Mark. Okay, let's see. What else do we have? Okay, so the following question is, okay, we want to select a subset of 5 people from the set of 15 junior students and a subset of 7 from the set of 16 senior students to form a committee. So how many ways are there to form such a committee? Okay, I'll give you a couple of minutes for you to try to solve it on your own. And then I'll do it for you. Okay. So let's, I know these are easy problems, but they're still kind of, I'll go through the thought process because I think it will help, because there are some things to kind of think about here. So, okay, so we are selecting these people from a committee, and we have to establish, are repetitions possible? Does order matter, right? So when you're putting people on the committee, usually repetitions are not possible because you cannot put the same person twice on the committee, right? You cannot copy a person. And now, whether the order matters or not, you have to be a little bit careful about that. So in this case, there are no roles on the committee, right? Committee is just a set of people. So in this case, the order does not matter. However, we've also seen, I think in lectures or maybe previous recitations, there are these types of committee questions where people on the committee have a role. There's like a president, vice president, or something. So in that case, you have to be careful because in that case, the order does matter. They're not just a set, right? Whether somebody is a vice president or president, it makes a difference. So be careful there. Okay, so here the order doesn't matter, right? So these are combinations. So we're going to choose first junior students. So we are choosing out of 18, 5 of them. And then we still have to choose out of 16 senior ones, 7 of them. So the solution is choose 5 out of 18 times choose 7 out of 16. Why is there multiplication between them? Well, we're using rule of product, because we are assembling these committees. So it's a multiplication and not an addition. Any questions about this one? Okay.
So maybe one question for me.
Go ahead.
I was thinking because you took 5 students out of the 18, like the next group, the 16 students, would instead be 13. I guess the 16 and 18 are separate, huh?
Yeah, exactly. So yeah, we had these problems when they're, you're choosing committee and they're kind of bunched together. So here, first you're choosing these 5 from junior students, and then you're choosing 7 from senior, and junior and senior students are separate. So that's why. It's a good observation. Yeah, it's another thing to kind of keep in mind. Any other questions? Okay. Okay. Let's see the next one. Okay, so how many license plates that contain numbers only consist of 6 digits? With exactly 2 of the same digits are possible. Okay, so we're looking for license plates with 6 digits, and then out of these 6, exactly 2 are going to be the same digit. So as before, I'll give you maybe this one is a little bit trickier. So I'll give you 3 to 4 minutes to try to solve it, and then we'll do it together. So think about the order matters, whether the order matters or not. And then, they need to have exactly 2 of the same digit. And also, if you have any kind of clarification questions about the problem, I mean, feel free to ask them right now. Don't have to wait until I solve it. So I like that you're posting solutions in the chat. Even if they're not correct, I might kind of pick some of them to point out some common mistakes. So it might be a good learning opportunity, even if they're not quite right. Okay, so let's do this. So the way to think about these types of questions, and they kind of, is this type where you have a sequence, but you have, you have a certain number of certain letters or digits. So the way to think about them is you have this license plates, which are sequences of 4 digits, right? 6 digits, sorry. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so first, we're going to place these 2 digits that have to be the same. So the way to place them is that we have to choose 2 slots out of these 6 in which we are going to put them. And so that's where we have combinations. So we are choosing 2 slots out of 6 in which we are going to put these 2 digits that are the same. So let's say we choose this slot and we put digit 1, and maybe we choose this slot and we put digit 1. Okay. Now we multiply this with the number of options that we have for these digits that have to be the same. And we have 10 options available to us here, because we can choose any of these digits from 0 to 9. Okay. So this now captures these 2 digits that are the same. And now we still have to multiply this with the number of possibilities that we have for these 4 leftover spaces. And the number of possibilities with this for these 4 is the same as just filling 4 slots from 9 digits. So we cannot use the one we already used to fill in these two spots. If we would use that one, then we would have situations where we would have more than two of the same digit, right? So it's going to be times permutations. We're choosing from 9, and we're putting them in 4 spots. Alternatively, you can write, I mean, if you calculate this, is going to be 9 times 8 times 7 times 6. So either of these would be fine solutions. In the second one, I use the rule of product, right? I have 9 digits I can put in the first place, 8 in the second. And then 7 and then 6. Okay, so that's the solution. There was one kind of interesting one from the chat. It was 10 times 10 times 9, 8, 7, 6. So 10 times 10 times 9 times 8 times 7 times 6. So that's one of the ones from the chat, and it's not correct. So for example, this one. So what does this first 10 times 10 means? It means you are putting any of the 10 in the first spot, and then any of the 10 in the second spot. So it means they can be different, and then you fill out the rest of them. So it's not going to lead to the correct solution. Okay. Any questions about the solution? Another maybe common mistake here would be, instead of choosing permutations here, that you say, times 9 to the power of 4. So this would not be correct, because you would allow license plate that have not exactly 2 of the same digits, right? You would allow more repetitions. So you would allow license plate that have 3 digits of some kind, and so on. Okay. Any questions? Okay. Let's see. Let's move to the next one. So how many possible sequences of 10 coin flips give exactly 3 or exactly 4 heads? So I'll give you 3 minutes to try to solve this. So one hint here, this OR is important. So there is this rule that we introduced that usually you apply when you see OR, right? So we compute flips with exactly 3 and flips with exactly 4, and then we have to do something with them. Okay. So let's solve it. So sequences of 10 coin flips are very similar to license plates. Basically, they're identical, except here you have only tails or heads, while in license plates situation, you had all the digits, right? And so, so the way to think about this, right? You have this sequence of 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of 10 slots, and you are putting, you know, H or T in each one of them, and so on. And so, so how many of them have exactly 3 H's? Well, you compute that by choosing 3 positions out of 10 in which you are going to put these 3 H's. And then the other positions you're going to fill up with T's. So, you know, it's just going to be times 1, or you can even leave that out. So that's the case when you have exactly 3 heads. And now, because there is OR between them, there's going to be rule of sum. And now we are looking for the ones that have exactly 4 heads. So it's almost the same as this, except you're choosing 4 positions out of 10, and then times 1 to put tails. So there's a solution for this one. To practice this a little bit, let's try to calculate it out. It's not that bad. So we have 10 factorial divided by 3 factorial times 7 factorial plus 10 factorial divided by 4 factorial times 6 factorial. And that is equal to, factorial is a reason to cancel. So, you know, you cancel 7 factorial with 10 factorial and you get 10 times 9 times 8 divided by 3 times 2 times 1 plus, similarly here, 6 factorial mostly cancels with 10 factorial. So up there you get 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. So 4 times 2 is 8, cancels with 8. 3 cancels here. 2 cancels here. 3 here. Okay, so we get 30 times 4, 120 plus 30 times 7, 210, and that is equal to 330. So that's the final result. Okay, any questions about this one?
Why are you multiplying both of them by 1?
Oh, it's so the algorithm for generating these sequences, it has 2 steps. So first I pick 3 slots for heads, and I place heads in those 3 slots. And then I have to to complete the sequence, I have to fill up or fill into the rest of the slots tails. And so this one captures how many different ways there are to put tails in the leftover slots. And there is just one, because you just put T everywhere. I mean, there is only one way of doing it. So it will be totally fine to drop this one. I just put it there because I want to be kind of completely clear, but we would totally accept a solution where you don't put out where you left out this one. So I hope that covers it. Any other questions? Okay. So let's skip this one. Let's see. So this one was from your homework. So let's do breakout rooms, solve all three, A, B, and C. I know in office hours, some of the students kind of struggle with this problem. We're choosing this sample of 6 and so on. So I think let's try to redo this and try to solve it on your own and discuss the solution with your peers. I know that there is I haven't really managed to solve this problem where the presentation disappears once I put you in breakout rooms. So you can maybe write down just the main facts. You have 100 computers, 4 out of these 100 are defective, and you're choosing a sample of 6. And now the questions are, how many different samples there are total? Out of these, how many samples contain all 4 defective computers? Don't compute the probability. Forget about the probability. You just want to answer this first part of the question. So we just want to do counting at this point. And see how many samples contain 1 or more defective computers. Okay. So let's do breakout rooms. Okay, so welcome back, everyone. Let's do this. Okay, so we have 100 computers. There is 4 defective ones in there. We're choosing a sample of 6. So does the order matter? No, we're just choosing a set of computers. It doesn't matter in which order we choose them. Are there repetitions? No, because you cannot choose the same computer twice, right? Once you choose it to put in the sample, it's there. So these are going to be our combinations. So question A, how many different samples are there? So the total number of samples, we are choosing out of 100 computers, 6 of them. So that's the solution for part A. Part B, out of these, how many samples contain all 4 defective computers? So how do you think about this part B? So, so all 4 defective computers have to be in your sample. That means, you have this set of 6 computers in a sample. So there is 6 of them here. And the first thing you do is you select this, you pull out these 4 defective ones, and you put them in. So in your sample, you are going to have your 4 defective ones. And so you still have to fill in these 2, right, to get a sample of 6 computers. So the way to fill in these 4, there is just one way to do this, right? You select these 4 defective ones and you put them there. And then times, you still have to do the 2 that are not effective. So now you're choosing 2 out of 96 because you remove these 4 defective ones. So that's B, part B. And then we're not going to do probability. We're going to do a lot of probabilities on Thursday. Part C, how many samples contain 1 or more defective computers? So a common, when you see 1 or more, a common pattern is to use the rule of complements. So instead of trying to do this directly and compute, samples that have exactly 1 plus samples that have exactly 2 plus samples that have exactly 3 plus samples that have exactly 4. An easier way to do it is to compute total and subtract from it the number of samples with 0 defective. So if you calculate this, you're going to get the count for this question. So we know what the total is. We computed it in part A. So we have choose 6 from 100. And then minus the number of samples that have 0 defective. So that means remove defective ones from the samples. And so we are choosing 6 from 96. So that is the solution to part C. Okay, any questions? So there is a question, would choose 4.1 times choose 99.5 work? I don't quite understand this solution. I'm sorry.
That's when I was thinking.
Go ahead.
I was thinking you choose one of the defective computers, and then you have to choose just 5 other computers from the 99 remaining.
Is that for part B or for part C?
Oh, sorry. No, part C.
Um,
Does that not make sense?
so let me think about this. So, yeah, I mean, I don't think that works. I don't have a clear explanation for why it wouldn't work.
I think that's the number of ways to have exactly one defective computer in your sample. So you need to calculate 2, 3, and 4.
Okay.
Well, what? So wouldn't the number? Wouldn't that be choose 4-1 times choose like 96 5 for the exactly one?
Yes, you are right. So good point. So the direct way of doing it would be choose 4-1 times choose 96 5 plus choose 4-2 times choose 96 4. I think I'm doing it right. Plus choose 4-3 times choose 96 3, I guess, and so on.
Yeah. But you don't think this solution would work?
The thing that you just if the solution is the only thing, just do what you wrote, I don't think that will work. That would not work.
Okay.
Would it work if you started like adding the choose 1 out of 4, choose 2 out of 4, choose 3 out of 4?
Yes, that will work. Okay. Okay. So we have to stop here. So thank you, everyone. And please join the discussion sessions on Thursday, because we're going to do many more problems, and Thursday is going to be all about probabilities. But both of these are going to be in quiz 5. Okay, thanks everyone. Bye.
Thank you.